In our previous lecture we were discussing about the convergence of the secant method. Let us briefly look at what we have done last time, so that we can derive the rate of convergence of the secant method. Now what we were trying to find was, we have to find the simple root of the equation f x is equal to 0. We have constructed the secant method as that we have two initial approximations xk minus 1 and xk. Based on that we are using the formula xk plus 1 is xk minus xk minus xk minus 1. In the denominator we have f of xk minus f of xk minus 1. This factor is multiplied by f of xk. Then in order to obtain the convergence rate, we are substituting for the errors in the solution, as epsilon k minus 1 is the difference between the exact solution and the estimate xk minus 1. Similarly epsilon k and epsilon k were defined. Then what we did was, we substituted the expressions for xk minus 1 from here as epsilon k minus 1 plus xi, epsilon xk is equal to epsilon k plus xi, xk plus 1 is epsilon k plus 1 plus xi. Then the denominator was simplified. We take this up to the numerator, put it to the power of minus 1, use the binomial theorem for expanding it. We have expanded the denominator in this particular form and multiply these two factors and finally cancelled out. Then we have simplified and we have seen that this is epsilon k square cancels here, and if I denote this by constant c, then I can write this as simply c times epsilon k minus 1. This was the expression that we have derived it, and now we would like to find in the expression for the error or the order of convergence that we have defined relates the error between at the step xk plus 1 and xk only. If any one of these formulas, for example secant, Muller, all of them would contain epsilon k minus 1, epsilon k minus 2, we must use the definition of the rate of convergence to reduce this into the form of epsilon k plus 1 is some factor epsilon k to the power of something. That power would be the rate of convergence. So what we would do here is, in order to get this particular result, I would just briefly write what we will do. I will have to get a formula of the type epsilon k plus 1 is equal to a into epsilon k to the power of p. This is the definition of the rate of convergence or order of the method. In order to eliminate epsilon k minus 1 that I have here over here, I would substitute k is equal to k minus 1. So I would get here epsilon k is equal to a into epsilon k minus 1 to the power of p. Now I will express epsilon k minus 1 back in terms of epsilon k. Therefore what I would write here is epsilon k minus 1 would be this to the power of 1 by p and a to the power of minus 1 by p. So I will have a to the power of minus 1 by p into epsilon k to the power of 1 by p. Now I am able to express epsilon k minus 1 in terms of epsilon k, and therefore I will substitute this in the expression that we have written over here, so that I will now have, let me take this expression as this, therefore I will have here epsilon of k plus 1 is equal to c. Let us substitute first epsilon k minus 1 here. So I would have here a to the power of minus 1 by p. This epsilon k is there, and now I have got epsilon k to the power of 1 by p. I have got epsilon k to the power of 1 by p. Now let us simplify this. This is c a to the power of minus 1 by p epsilon k to the power of 1 plus 1 by p. But by definition epsilon k plus 1 should be equal to a into epsilon k to the power of p. So this should be equal to a into epsilon k to the power of p. Therefore the constant that must be equal, the powers should be equal in order that this is an identity. Therefore I will have p is equal to 1 plus 1 by p. We will equate the coefficients in a moment. So the power should equate, therefore p is equal to 1 plus 2 power. Now let us try to solve this. This gives you p squared minus p minus 1 is equal to 0. So I am taking everything to the left hand side. Solve for p. The value of p will be equal to 1 plus minus a root of 4 plus 1 5 root 5 by 2. Now, the power that we are using here in the definition is a positive quantity. Therefore, after the two roots I will choose which is the positive quantity, and that is your 1 plus root 5 upon 2. If I evaluate this, this is approximately equal to 1.618. Therefore, the order of the secant method that we have P is 1.618. Therefore, we will call this as order as 1.618, and we shall call this as super linear convergence between linear and quadratic. So, I will call this as super linear convergence. Now, we would like to look at what happens to the constant. The constant should be equal. So, that means I should have A is equal to C into a to the power of minus 1 upon P. So, I should have here A is equal to C a to the power of minus 1 upon P. Now, or bring everything to the left hand side, that is A to the power of 1 plus 1 upon P is equal to C, and I want A in terms of C. So, we would write this as A into 1 plus P by P is equal to C, or A is equal to C minus P upon P plus 1. Therefore, we have determined both the error constant as well as the order of the method. So, the relationship between the constants that we are using in the secant method, the error constant the error constant in the secant method was C, and this is the error constant for the method that we are defining. So, we have defined the method as epsilon k plus 1 is A into epsilon k to the power of 1.618. So, and this A is given by C, where C was defined as half of f double dash by xi by f dash xi. So, this is the relationship that I can get here. Now, I can similarly obtain the order of convergence of all the remaining methods. I will leave it as an exercise for you. The methods, let me write down the put it over here. Now, the order of the Chebyshev method and the multi-point methods are 3. Whichever the multi-point method that we have used, if you remember, we have derived two multi-point methods. The one multi-point method was using one function evaluation and two derivative evaluations. The other multi-point method was using two function evaluations and one derivative evaluation. Depending on the cost of the evaluating of the function or the derivative, we can choose the proper multi-point method to find the solution in the problem. Now, the order of the Muller method is 1.84. Now, so far we have, when we said the talked of cost of these methods, we were counting the cost. Major cost was the function evaluation. The other part or multiplication divisions are too trivial or too less, therefore, the major cost was only evaluation. In that sense, Chebyshev and multi-point methods require 3 evaluations, Newton-Raphson method requires 2 evaluations, Muller and secant method requires 1 function evaluation. Now, the attempts were made to compare these methods to look at in a different perspective, and one particular perspective was what they called as efficiency of a method. It is a very simple definition which is not rigorous, of course. We cannot strictly based on this, we cannot say a particular method is good or bad, but there is a way of looking at defining a efficiency of the method. It simply defines that you take P order the method, count the total number of evaluations n, that means function as well as derivative evaluations, then take the root of that, that is P to the power of 1 by n, and that shall be called as the efficiency of the method. If this quantity is big, of course, it's instead of taking this, you can as well take logarithm, it's one and the same thing. So, if this number is large, then we say that the efficiency of the method is better. But I should say that this is not a rigorous way of approaching, it is only the it is only a way of looking at these methods, and this was given by an author called Traub. Now let us just look at just put it in a tabular form what we have done so far in the methods. So we shall assume that the cost of evaluating f dash double dash are the same. So that means we are equally the computational cost of derivative evaluation, second derivative evaluation and function is the same. Then we have this particular table of values. If you look at the secant method, it has only one function evaluation, and we have shown that the order is a 1.618, that is approximately 1.62. So I will take the nth root of 1.62, nth root, that is 1th root, that is 1.62 itself. The Newton-Raphson method has two evaluations, one function, one derivative. So total is 1 plus 1, we will take it as 2. The order is 2, therefore efficiency is the second root or the square root of 2, that will be simply 1.41. In the Chebyshev method, we have one function, one first derivative, one second derivative evaluation. So the total of 3 evaluations, the order is p. So the efficiency index is cube root of 3, this is n, this is cube root of 3, that is 1.44. The Muller method is, there is only one function evaluation, the order of the method is 1.84, therefore efficiency index is 1.84. The multi-point also has got 3 evaluations, either one function 2 derivative or 2 derivative 1 function evaluation. So again we have cube root of 3, that is equal to 1.44. Now from the viewpoint of Traub, it looks as though Muller method is the best because it has the best efficiency index, but however if you look at the total computation when you are going about, the other methods would score because there are other factors besides just looking at this particular way of looking at. Therefore from this, as I said, this is one way of looking at, but this does not say that Muller is the best method for computation. Now for example, you can look at the whatever we have discussed here can be looked at a slightly different way. We have said the cost of evaluating f dash f double dash are the same. Suppose the cost of evaluating derivative is less or the cost of derivative is more, then what are we are talking about will be going to different. So let us suppose f and f dash, the evaluation, the cost is different. So let us take the cost of evaluating as 1 and the cost of evaluating f dash x be some omega. So we can always find the ratio and then say 1, and we can normalize the evaluation of f x to 1, and then evaluation of f dash x will be some omega. For Newton-Raphson method, n will be equal to 1 plus omega total cost, that is evaluation of f x and f prime, 1 plus omega. Now let us take the logarithm on both sides because it is easier to look at that, because we have got the power now is a fraction, therefore we need to take a logarithm. So if I take the logarithm of this, we will have logarithm of e star, that is logarithm of nth root of 2, that is n is 1 plus omega to power of 1 upon 1 plus omega. This I can write logarithm of 2 divided by 1 plus omega. If I look at the same quantity for secant method has no evaluation of f prime, therefore whatever we have got earlier would remain as it is, logarithm of e star is logarithm of 1.618. Now what I am trying to do here is to say when will the Newton-Raphson method be better than secant method. If I can say the cost of f x is something, cost of f dash x is something, which one do you think that Newton-Raphson or secant would be superior, or under what circumstances the Newton-Raphson method would be superior. Now if the Newton-Raphson method is to be superior, then this quantity should be greater than this quantity because efficiency index should be bigger. So we should have logarithm of 2 divided by 1 plus omega should be greater than logarithm of 1.618. Let us simplify this. Logarithm of 2, I bring it to this side, is greater than 1 plus omega, or omega is less than this quantity minus 1. So if I just evaluate this, I get it as 0.44. Therefore from this we can conclude that if the cost of evaluating f dash x is less than 0.044 into cost of evaluating f x, we say earlier we normalized it as f x as cost is 1, cost of evaluating f dash x is omega. Therefore if I take the f dash x evaluation, cost of evaluation is less than 0.044, into cost of evaluating fx, then Newton-Raphson method is superior. As I said, this is only a way of looking at it. If you find that the first derivative and second derivative can be evaluated easily, Chebyshev method would definitely score because it is a third order, and we have seen what we mean by the order of a method. The error is of the order of 3, that is epsilon k cubed, and if at any time you are within the bound when once the interval in which the root lies, that is your error epsilon k is less than 1, the convergence is going to be very, very fast. Now, however, in many practical applications, because the second derivative evaluation may be very difficult, the Newton-Raphson method found out to be the most popular method because of the reasonable value for p, that is the second order quadratic convergence, and the cost factor. The cost factor is one function evaluation, one derivative evaluation. You can see that even today in many of the problems, research problems otherwhere, wherever you need the roots, they would go to Newton-Raphson method than the other methods. Where of course the derivative is just not possible to be found, then they go to the secant method or the further modifications of Newton-Raphson method, in which we can only use fx and not a derivative at all. Now, there is yet another concept of defining a numerical method for solving the obtaining the simple root of an equation, and that is called the general iteration method. Here we take the equation fx is equal to 0 and solve it as x is equal to fx. There can be infinite number of possibilities. Given a method fx is equal to 0, you can write it as x is equal to fx. So, anyway you can write down and write the general method straight away as the xk plus 1 is phi of xk. Now, if you remember in the second lecture when we started the definition or defining an iterative method, we have taken a simple example. We have taken a simple example of a naught x square plus a1 x plus a2 is equal to 0, and then said that we can write an iterative method for solving this in any of these formats. If you, we may just look at what we have really done here. What we have done here is we have taken a2 plus a1 x to the right hand side divided by a naught xk and written a method like this. Alternatively, we said that I can retain the middle term here and then take these two terms to the right hand side. A division would give me xk plus 1. And similarly, in the third case we have taken a2 to the right hand side, we have taken common factor x between these two and then divided it out and brought a method. So, these are all of the form of xk plus 1 is equal to phi xk, which we can call it as a general iteration method. However, it will be, because it is there are, as I said, there are almost infinite number of ways that one can write this, because you can add x, subtract x if x is not available. So, it is a way of writing it. Therefore, it is necessary that we start iterative procedure to look at whether our choice of phi xk is correct or not. If the choice of phi xk is correct, divergence will be there, and if the choice is correct, the convergence will be there. So, let us first of all look at what is the condition on phi x such that the iteration converges. We shall call this phi x that we are using as an iteration function. So, everything depends on this iteration function. The convergence of the method depends on the function fx. Whatever we are discussing about the convergence is identically same as what we have done for the finding the convergence of the numerical methods, other numerical methods. So, we define the error as epsilon k is xk minus xi. The exact solution satisfies x is equal to phi x is the given equation. So, exact solution satisfies xi is equal to phi of xi. So, from this I will now substitute this definition here, so that I will have here xk plus 1 minus xi. I am now writing the I am substituting this definition into the method that we have just defined, that is the xk plus 1 is equal to phi of xk. We take this and take this, subtract these two, xk plus 1 minus xi on the left hand side, on the right hand side phi of xk minus phi of xi. I have subtracted these two to get xk plus 1 minus xi is equal to phi of xk minus phi of xi. Now, I will use the Taylor series expansions to find out what is the condition on phi x such that this method converges. So, let us open it up, phi of xi plus epsilon k by Taylor series. I will have phi of xi epsilon k phi dash of xi half epsilon square phi double dash of xi plus so on minus xi. Now, we do not need to write down more terms than this. Now, phi of xi and phi of xi cancels here, and therefore, what is left out is simply this term and this term. Furthermore, xi is equal to phi of xi, the exact solution satisfies phi of xi. No, we have phi of xi has already cancelled. Now, this definition of x k plus 1 minus xi is epsilon k plus 1. The right hand side is given as some a 1 into epsilon k, a 2 into epsilon k square. So, I have rewritten this particular step as epsilon k plus 1 the left hand side, a 1 into epsilon k, a 2 into epsilon k square plus order of epsilon k cubed, where a 1 is this first term phi dash of xi, a 2 is the second term phi double dash by 2. Therefore, in the case of this general iteration method that we have described in this particular way, I can write down the error on the current step as equal to a 1 epsilon k plus a 2 epsilon k square plus order of epsilon k cubed. Now, if a 1 is not equal to 0 in a method, then the error is can be written as simply you see, if in one case if we have a 1 is not equal to 0, then I can drop all these terms and write this as epsilon k plus 1 is equal to a 1 into epsilon k. Therefore, this will become, therefore, in this case p is equal to 1, this is p is p to the power epsilon k to the power of 1. Therefore, the order of the method is 1. Therefore, when a 1 is not equal to 0, I would get a first order method, because in that case epsilon k plus 1 is equal to a 1 epsilon k, that is epsilon k plus 1 a plus epsilon k. Therefore, the order of the method will be 1. But now let us proceed on. I will just show this transparency, but let me write it down here. Let us put k is equal to 0 here. So, I will have epsilon 1 is equal to a 1 epsilon 0. I put k is equal to 0. Then let us put k is equal to 1. Therefore, I will have epsilon 1 a 1 epsilon 1, but epsilon 1 is a 1 square epsilon naught. Now, I proceed, epsilon 3 is a 1 epsilon 2. Therefore, this is a 1 cubed epsilon 0. Therefore, if I proceed on like this, what I would get is epsilon k is equal to a 1 to the power of k epsilon naught. So, we repeatedly do this, and then I produce this epsilon k is a 1 k epsilon naught. Now, we can see that if this method is to converge, epsilon naught is the initial error, the error of initial approximation. If the initial approximation is to decay, the error in the initial approximation is to decay, that it goes to 0, then epsilon k should tend to 0. The only possibility is, as k tends to infinity, this is to go to 0, means magnitude of a 1 should be less than 1. Therefore, if magnitude of a 1 is less than 1 and epsilon naught is not large, of course it is always finite quantity, even if it is 2 or 5 or 10, it does not make any difference, then epsilon k will tend to 0 as k tends to 0, k tends to infinity, and convergence is obtained. Therefore, the condition for the method to converge is magnitude of a 1 should be less than 1. So, let me use this same transparency again. Therefore, we require magnitude of a 1 is equal to magnitude of phi dash xi is less than 1, where xi is any value lying in the open interval a b. However, xi is an unknown quantity. Therefore, we shall approximate the magnitude of phi dash of xi by the maximum magnitude of phi dash x in the closed interval a b. That means, we will approximate phi dash of xi by the maximum magnitude of phi dash of x in the closed interval a b. This approximation is valid because xi is any value in a b, and hence phi dash of xi in magnitude is always less than or equal to maximum magnitude of phi dash of x. That is, phi dash of xi is always less than or equal to maximum of phi dash of x, x lying in the interval a b. Therefore, we shall require that magnitude of a 1 is approximately equal to maximum of phi dash of x, x lying in the interval a b is strictly less than or equal to a value, finite value c, less than 1. Hence, the iteration function should satisfy the condition, this condition for all iterates, so that the iteration sequence converges, otherwise it will diverge. Now, the in all the numerical methods that we have to do many experiments to see whether our solution is correct or not. If you look at the solution of an ordinary partial differential equation or a system of ordinary partial differential equation whose solution is not known, then we are solving it with a particular step length. We have produced some solutions. We have to be sure that what we have produced is not junk. We have to say that this solution is approximate solution. So, what we normally do, we repeat the same computation with another step length and produce new solutions. Now, if these two solutions are reasonably close to each other, or if they are not reasonably close to each other, what can we do? So, if you want to solve this by still smaller step length, we have already made some expense or some computation has already been done. Does this computation that we have already done goes waste? Is it possible for us to manipulate or use this result to get a higher order result, a better result? The answer is yes. None of these values that you have obtained in numerical this thing need to be put in a waste basket, but we can use them to produce much better results. The concept is lies in what we call as acceleration of linear such the concept is called extrapolation, which we shall do later on in the both in numerical differentiation, numerical integration, everywhere we use the concept of extrapolation. So, the idea of extrapolation comes from what we are talking about. We shall call this as acceleration of linear convergence. Now, we start over with the method xk plus 1 is equal to phi xk. Now, what we are saying is that we want to manipulate the computed result of successive approximation to produce a better result. That means, I would like to produce a new value by manipulating such that the new value is obtained as if it has been obtained from a higher order method, not in this case for example first order method, it is as if it is obtained from a second order method. How do we do is a very simple manipulation. Let us assume that 3 approximations are available for us, that is xk, xk plus 1, xk plus 2. Starting with this we have x0, x1, x2. So, we have computed with a first order method x0, x1, x2. What will be the error looks like? By definition, error looks like epsilon k plus 1 is a1 epsilon k and epsilon k plus 2 is equal to a1 epsilon k plus 1. This is how the error looks like. Now, if the method is to behave like a second order method, the error term should be epsilon k plus 2 is equal to some constant epsilon k square. That means, the first order term should not appear in this. So, what we do now here is we just divide these two expressions. So, I divide it out. So, epsilon k plus 1 divided by epsilon k, I am equating a1, epsilon k plus 1 divided by epsilon k is equal to epsilon k plus 2 divided by epsilon k plus 1, that is we have equated a1 on both sides. Now, cross multiply epsilon k plus 2 into epsilon k is epsilon k plus 1 square. From here I would like to retrieve a numerical method, work backwards by using the definition of epsilon k plus 1, epsilon k plus 2. This numerical method, whatever is retrieved from here, is obtained by eliminating coefficient of epsilon k, that is the first order term epsilon k. Therefore, the numerical method that we have here, when expanded in Taylor series, will be starting with epsilon k square because a1 has been eliminated. So, whatever method I retrieve from here would be as if it is a second order method. Now, let us simplify this. I am substituting epsilon k plus 2 as xi minus epsilon k plus 2 and epsilon k is xi minus epsilon k. This is equal to epsilon k plus 1 whole square, that is xi minus epsilon k plus minus x k plus 1 whole square. So, we are just substituting the definitions of this. Let us open it up. This is xi square, xi x k plus 2 plus x k plus 2 into x k. On the right hand side, let us take the square of this, xi square minus 2 xi x k plus 1 plus x k plus 1 square. Now, we can see xi square cancels both sides, xi square cancels both sides, and therefore, I bring this xi to this side and this x k plus 1 to the left hand side. So, I will have here xi x k plus 2 plus x k, these are the two terms, minus 2 times x k plus 1. On the right hand side, we will have x k plus 1 into x k minus x k plus 1 square. So, I am able to get xi alone because xi square has been cancelled. From this, I will now write down my next approximation. Now, I can write xi as, now from here I will take this to this side and write this as x k plus 2 minus x k plus 1 whole square divided by x k plus 2 minus twice x k plus 1 plus x k. Now, I would write this in the form of, in all the methods we are writing x k plus 1 is equal to x k plus something. So, I would like to rewrite this in the format as x k minus a quantity, some quantity g x or some quantity we are writing. So, I can simplify this and write it as x k minus x k plus 1 minus x k whole square divided by this same denominator x k plus 2 minus twice x k plus 1 plus x k. Now, we are going to define in our later lectures the meaning of these quantities that we have written here, delta of x k, delta square of x k. I denote this delta x k as x k plus 1 minus x k, and I denote the denominator by delta squared x k, that is definition of delta squared x k plus 2 minus twice x k plus 1 plus x k, and these are called the differences. They are called the first and second order differences, which we are going to define later on what is the difference, and for the moment let us take it as first and second order differences, just the name of these two quantities. Therefore, I will take the new approximation to xi as x star k, that is x k minus delta x k whole square by delta squared x k. Now, if I want to use this computation, I need 3 values first to start it, that is x k plus 1, x k plus 2. When once I have 3 successive approximations, I can now build up a new value called x star k, which will behave as if the result has been obtained from a second order method, because as I explained earlier, we have eliminated a1. When once you have eliminated a1, in the Taylor expansion it was containing epsilon k plus 1 is a1 epsilon k plus a2 epsilon k square and so on. If a1 is eliminated, the resultant is epsilon k plus 1 is equal to sum, instead of a2 will have sum c into epsilon k square. Therefore, this is a second order method, it would behave like a result as if it has been obtained by this one. How do you implement computationally? We start with x0, x1, x2, then we compute this. Now, this is a new better estimate. Now, I will use now this as my starting point, x3 let us say, x4, x5 I will compute again for the first order method. Now, I have got x3, x4, x5. Now, I go back to this method, compute it. So, after every 3 values, that means 2 new values and the value that we have here, with 3 of this we will now go on this one. So, each of these results will be as if it is second order method, that means somewhere in between we are doing the mid course correction to make it a better estimate or better value. Okay. Now, let us take an example on this. Now, I will take it as a we will perform 2 iterations of the linear iteration method, followed by 1 iteration of Aitken's delta squared method to find the root of x cubed minus 5x plus 1 is 0, and we shall use the initial approximation x0 is 0.5 and we shall repeat this process 2 times. That means we start with x0, x1, x2, then I use these 3 values to get the next estimate and then go on repeating it same thing 2 times. Now for this I need the values of f0, that is 1, f1 is -3, so that I am first estimating the where the root lies. The root lies in 0 and 1. Now the first thing that we will have to do is we have to construct our method from here. What I have done is here I have taken here x cubed plus 1 to the right hand side, take x as the middle term here and written it as x is 1 upon 5 x cubed plus 1. Therefore our method would be, if from here if I write, the method would be xk plus 1 is equal to phi of xk, that is your 1 upon 5 xk cubed plus 1. Now before we proceed using for computation, I would like to test whether our phi x iteration function is satisfying the convergence criteria or not. Therefore I need to check whether phi dash x in the interval in which the root lies is less than 1 or not. Now I can differentiate phi and get phi dash x. Phi dash x will be equal to, from here, (3 by 5 x squared). Now I need phi dash of x 3 by 5 x squared in magnitude, maximum the interval in which the root lies is 0 1, the interval in which the root lies is 0 1. So I want the maximum of this phi dash of x as this, and this obviously is less than 3 by 5, that is approximately 0.6. X is lying between 0 and 1, therefore it is, therefore this is strictly less than 1. Therefore this iteration is going to converge and is going to converge quite fast. The reason being, if magnitude of the particular number that we have taken, magnitude of a1 to the power of k tends to 0 and k tends to infinity, it will go to 0 very fast provided this a1 is small. Now if this quantity was say 0.1, then we can achieve convergence very fast. Now this quantity 0.6 is not bad, it is quite good, because the square of this is going to 0.36 and it is going to be reduced quite fast. Therefore this is an indicator as to how fast our method is going to converge. Now let us just compute these values. Now I would just get the values of, starting with x0 given to us 0.5. Now I would get x1, simply just substitute phi of x0 is equal to 0.5, phi of x0, that is 1 by 5 0.5 whole cube plus 1, just simplify 0.225. I then find phi of x1 and call it as x2, and that is 1 upon 5, this is 0.225 whole cube plus 1, that is equal to 202278. Now at this stage the value of x0, x1, x2, 3 values are available for me. Now I can use the Aitken's method to get a better estimate of the computation, and that will be, I will be using the, we call it as x0 star. You see, this is, you can indeed call it as x3, you need not call x0 star, you could as well call it as x3. In continuation we can call it as x3 also. x3 will be x0 minus, if you just go backwards and write down, substitute the values of k is equal to, now in this I am substituting k is 0, so this is x0, x1 minus x0, x2 minus 2x1 plus x0. So that is what I had written here. So this is the approximation. Now we have the values available for us, x0, x1, x2 values are available to us. So let us substitute these values here and simplify to get 0.200232. Now what we are claiming now is that this value is a value as if it has been obtained from a second order method, not from a first order method. Now we use this and then proceed on to find the, repeat this, x1 star is equal to phi of x1 0 star. You could as well call this as x4, you could as well call this as x5. There is no, I mean, hard and fast rule you should define them as that. So, we can go in a sequence x3, x4, x5. We remember that x3 was the update of the value to the next higher order. These two are obtained from the first order. x1 star is phi of x0 star. Now, I substitute this 1 upon 5 x cubed plus 1. So, I have a value x4 as this. Then I proceed further, x2 star is 1 by 5 0.201606 whole cubed plus 1. So, I compute this as x5. Now, this is the updated value. Now, I computed two values x4 and x5. Now, we are ready for next Aitken's acceleration convergence application. So, I can now use this x0 star, x1 star, x2 star to now use the method and write the next. Why don't we use no the current. So, we are now, what is the current estimate? The current estimate is x3, current estimate is this value. Now, I should proceed further, because the what is our iteration method? Iteration method connects only xk plus 1 and xk. Therefore, since x3 is available for me, I will now use x3 to get my x4, right. Now, whenever 3 values are available for me, I will go for the Aitken's method, because it needs 3 values to have an update. So, now once I have done x3, I will compute 2 values x4, x5. Now, I got x3, x4, x5. Now, what you are saying is that why not we take x2, x3, x4? No, reason is the previous value is a first order, this is a second order, this is a first order, and that will be a mismatch. So, therefore, we will start from this value only and then go ahead for 2 steps x4 and x5. This is a second order result, this is 2 are first order results. Now, I will manipulate these 3 to get a second order result. Therefore, I have now called this as this. You could as well call it as x6. So, next value is x5, x6. So, this will be x0 star, x1 star minus x0 star square, x2 star minus twice x1 star plus x0 star, and now we just substitute these 3 values to make the computation. So, I can compute this and get the test 200232 minus 201375 whole square minus 001342 is equal to this value. Therefore, it is possible, I mean, what we are really trying to show here is it is possible for us that whenever we get we have a method and we can analyze the method and get the error expression for it, it is possible for us to manipulate the computed results to get the results, computed result which is of higher order or superior to what we have. Very often we will see later why such a technique is to be used is if you go to try to find the derivative of a function which defines a table of values. That means, we have got a table given to us, it represents a function f(x), but I want what will be the derivative, the slope of the curve at any particular point. We do not know that the slope exists or not, we do not know how well the curve behaves for the function. Therefore, derivative finding is it could be an unstable process. Therefore, in such cases what we do is we will try to find a value for the derivative using a very lower order method which will always work. Then we would like to manipulate or extrapolate as we have done here to get as if you are getting from a higher order method. Why it should be done is that, as we have discussed earlier again, if you have a first order method, error is of the order of c into epsilon to the power of 1. Now, each iteration will give you at the most 1 decimal place. That means, if the error was 0.6, we can expect 0.5 or 0.56, next one you could expect at the most 0.47. Therefore, you need hundreds of iterations or maybe thousands of iterations to arrive at a accuracy of 10 to the power of minus 5 or 10 to the power of minus 6, and which is too expensive. Therefore, if you are able to jump from a first order to a higher order method at some stage or still higher order method, then you are avoiding few hundreds or few thousands of iterations to get the required result. That is why we need this kind of manipulation. And second comment is that most of these results that we are getting, they are not useless, even though they are results which are not at all accurate, they can still be manipulated to arrive at a much better results. Now, the methods that we have discussed so far can be used only for a simple root, that is, root is only simple. In most of the cases, you do not know in a particular problem whether the root is a simple root or a multiple root, and you are using Newton-Raphson method. The Newton-Raphson method is supposed to give us to the quadratic convergence. So, after few iterations, after at least few iterations, you will be able to see, if you take a printout of this, you will be able to see how that is going to converge. If you find that these results are not converging quadratically as it should be, I mean you are not getting that, that means there is something wrong in the procedure, not the method, but there is something wrong in the assumption that it is a simple root, maybe it is a multiple root. If it is a multiple root, the methods that we have used, all of them, its accuracy falls down. The Newton-Raphson method would no longer behave a quadratic method, it will behave like a first order method. Therefore, if the computation value, if the secant method also the same thing happens, it is superlinear, but it drops still further, so it will go below 1 or below that, you may not even get 1 place of accuracy in the secant method. Therefore, this thing worsens if the multiplicity of the root is still higher. It's a the degree of 3 or 4 or 5 you have got the root, then this situation worsens further. Then what is the solution for such case when you have a multiple root and not a simple root? And as I said, it is visible for you in the computations whether the solution is coming or not, or when there is a difficulty is clearly visible for us in the solution that we have obtained there. Therefore, we will have to modify the methods that we have done. We are not going to do new methods, but they modify the method that we have done in order to take care of obtaining the multiple roots. Now, the one this particular part I will take it later in the next lecture, but let me just the simple application of this. This we have discussed, this part I am saying we have discussed earlier. When we defined a simple root and a multiple root of multiplicity m, if I differentiate that function, that f dash x is equal to 0 will have multiplicity m minus 1 of the same root. Therefore, we have shown that if I construct a new function hx is equal to fx upon f dash x, then hx will have a simple root at x is equal to xi, right. Say fx has got say a root of multiplicity 4, its derivative will have a root of multiplicity 3. Therefore, its ratio will have a root of multiplicity 1, that means it will have a simple root. Therefore, since this hx has a simple root, then I can use Newton-Raphson secant any method, Chebyshev method on hx, which will produce me the required result of the same order as we are claiming there. Therefore, I can use this, use the secant method, use the Newton-Raphson method and all the other methods. I think we will stop at this today, but we will see, but why do we need new methods, modify the methods if I can use this method? We shall show that yes, we can use it, but you will have to spend little bit more computer cost. That means we will show that we have to evaluate one more quantity. Newton-Raphson method was using only f and f dash, but now we will show that we need second derivative also if you want a Newton-Raphson method, but with this approach. That means the cost of computation will go slightly higher, but then we can definitely use the Newton-Raphson method using this particular method. Thank you. We will stop today.